we're using this as an excuse to investigate a notion of weak solutions to the binomial partial flow, where we really just ask that this identity be satisfied. And so we sort of define a very general setting. The setting, I think I called it oriented variables, in which we can make sense of the terms in the setting, which is the identity in the box here. We define the setting in which we can make sense of that, and then we ask, what can we say if we assume essentially only this, and that the object is closed in a sort of a weak sense, in a natural weak sense. And okay, there are a couple other conditions. Okay, so then I gave you some examples of weak solutions that are not smooth solutions. For example, two things that annihilate each other. Conserved quantities. What I was doing at the end was introducing was this, and so here's the plan for today. So the goals for today. One is a continuity in T of weak solutions with respect to a weak norm. And then first we have to, let's get more detailed color, so let's then discuss this. This is kind of interesting. And then maybe existence of weak solutions. And then I'll start on the weak, strong uniqueness. So I think I'll just state an existence theorem without giving the proof, and I'll show a video. Okay, good. So that's the, and so we had started this program, this first topic on Monday. I had introduced this weak norm, and the definition is up above. And so this is sort of a, if you like, geometric measure theory. And so this is so geometric measure theory in general is this approach to geometric questions in which one, so if you're like motivated by the idea of, you know, in the 40s, 50s, 60s, people realized it was useful to understand PDEs in not just in the classical sense, but to introduce spaces of weak solutions and so on. And so this is the attempt to do the same for geometric problems, where one would view submanifolds as measures or distributions or something like that. Okay, and so a natural norm you see all the time in the setting is this one I've written here, the homogeneous flat norm. And okay, and so I want to discuss some properties of this norm and then prove a continuity, prove that the weak solutions evolve continuously in a certain sense with respect to this norm. And again, I'll give sort of a simplified proof just to illustrate the main idea. Okay, so the homogeneous flat norm. Okay, so here it is. So I've written this for a difference of two. So again, let's go over this more slowly. So let's say T is a closed. Okay, what's a closed 1D current? Which was, so for our purposes, we can think of this as being vector valued measures. So if I have a vector valued measure, I can integrate against a vector field. And so 1D currents we can identify as vector valued measures. There's a kind of a, okay, there's a kind of a more dogmatic or axiomatic approach to geometric measure theory in which I would distinguish between these, but let's keep it simple. And closed would say that the integral of phi dot t of dx, it's in the same sense we described before. The integral against gradients is 0 for all phi C1 with compact support vector fields. Okay, and so then the canonical example of a closed 1D current is just the integral, is the measure associated integration around a oriented ellipsis closed curve. Okay, and so then, and so again, if I look at t minus t prime, for example, well, actually, it doesn't have to be a difference. So let's just say, so later on, I'll be interested in using this as a norm, but let's just, as a metric, but now let's just define the norm of t is the supremum of the integral of phi dot t of dx, where I consider all phi such that the curl of phi in L infinity is less than 1. Okay, and so the point is there's a nice geometric description of this. Let's see, there's a message here. Oh, okay, so yeah, so that'll be available eventually. And so the, okay, so here this is closed. Means that. Okay, and so then let me see. So here's the picture. I'll state the lemma in a second. So the picture is that if I have, so let me picture a closed 1D current as an oriented curve. So say this is t, and I have another t prime. And so then the norm of, and I should put an F here. I think that's what I called it. Oh, I put an F dot for some reason. So then the F dot norm of the difference is essentially the, so it will be the area of the smallest surface whose spans, I look at two-dimensional surfaces whose boundary is t minus t prime, boundary in the sense of Stokes' theorem. Okay, so I won't quite prove this, but I'll prove that this is maybe a less than or equal to the area, so the minimum of the area of S where the boundary of S is t minus t prime. Okay, and so so this is a nice, it's an interesting thing. It's a sort of natural from a geometric point of view. And so this is what we'll show. And so because I'm phrasing all this geometric stuff in terms of measure theory, I think of t as being integration around the curve, the first curve drawn, and t prime as being the integration on the second curve. I also want to think of S as being integration over the two-dimensional surface. And so the lemma says that. Says that the, okay, and I'll write this just for single current t, but it could be the flat norm, the homogeneous flat norm of t is the infimum of okay, S of R3, where S is a measure. And the curl of S is equal to T. And so the relationship between what I've written here and the above picture is, and I should say, I'm doing this all in the language of vector calculus for simplicity. In some way, it makes more sense if you use the language of differential forms. And so the differential forms and integral currents and stuff like that, but let's not do that. Okay, so the point is, in the above picture, if I have a surface, so the point is, in the above picture, so a surface S may be identified with, well, the operation, if I can, so what I want to identify with a vector valid measure, and a vector valid measure is something I integrate, I can integrate a vector field against a vector valid measure. And so the natural way to integrate a vector field against a surface is the one we teach in vector calculus. So it's the operation that takes a vector field phi to the integral of phi dot the unit normal d surface area, which is a vector valued measure. And then Stokes' theorem, in exactly the form that we teach it, would say that the curl of this, so then I should have used a different notation. Okay, imagine that I have two different S's here. Actually, let's change this to I think above I called it new. So here it's S and here it's new. And let's call this, sorry, my notation is terrible. Let's call this that n the unit normal. Okay, and so new is the vector valid measure, corresponding to 0 is S. Okay, and so then the integral of phi against the curl of nu by definition is the integral of the curl of phi against nu. And again, by definition, that's the integral of the curl of phi dot the normal d surface area over S. And that's the integral of over the boundary of S of phi in the Stokes theorem, phi dot the unit tangent. Okay, and so this is, so you see, if I identify a surface with a vector valid measure in the sense I've written, then the curl of that vector valid measure is exactly the boundary. Okay, and so, right, and so again, the, right, and so this condition that the curl of nu is T is saying that T is the boundary, the geometric boundary of nu. Okay, and so then that's just to explain the lemma. Let's see if we can prove it. So let me let's recall how this goes. There's always there's an easy way and a hard way, and so so what's T, the flat norm, is the supremum of the integral of right. Just recopying the definition, phi dot T of dx, where the curl of phi is less than 1. So if T is the curl of nu, then, well, then clearly for any phi, the phi dot t, the integral, is phi dot the curl of nu, the integral. And so the curl of phi dot nu, and this is less than the L infinity norm of the curl of phi. And then, okay, so when I write this nu of R3, this is the total variation of nu. This is kind of the definition. And so if, in particular, in the instance where nu corresponds to integration over a surface, then this total variation will just be the area of the surface. Okay, and so this proves half of what I want to show. And so, so taking the supremum will show that T homogeneous flat norm is so if I then take the supremum over all phi such that the curl of phi in L infinity is bounded by 1, I'll get this is less than the infimum of nu of R3, where the curl of nu is equal to T. And so the other side is the other direction is a bit harder. Let's do that. So what I'm doing here is kind of a standard argument that you may have seen. Anyway, it's a nice argument. The other direction. And so it uses the Hombotic theorem and duality. So the other direction. I found this a bit opaque the first time I saw it, and so you may have had the same reaction, but it's an elegant proof. So, okay, so let's define, I want to define two spaces, say X will be the continuous space, the continuous vector fields on R3 who decay at infinity. So the subscript means decay at infinity. And with the sup norm or the max norm, really. Okay, Bonnet space. And Y will be the set of, say, let's call them psi in X, such that psi is a curl. And so I want to, what I'll do is I'll define a bounded linear functional on Y. So Y is a closed subspace of so Y is a closed subspace of X. That's pretty easy to see. If I have a limit of things who are curls of C1 functions, they'll again be a curl of a C1 function. They'll always be orthogonal to gradients, for example. That's easy to see. And so now I'll define a linear functional L from Y to R linear. And I'll say that if L acting on the curl of phi, so everything in Y has that form, is equal to, and so what's, let me remember what I'm doing. So, so I have I'm given a T, and I want to, I want to prove the other inequality. I want to prove that T is bigger than this, that the flat norm T is greater than what's infimum. And so T is there, and so I'll say this is the integral of phi dot T of dx. Okay, perfectly. So this totally makes sense for curl for say psi being the curl of phi in Y. And so note, what's the norm of L? And so I want to use the, so L, I want to use the norm, L is a closed subset of X. I want to use the norm X to R. This is the supremum of L of phi, where L psi, say, where the norm of psi is less than 1, the X norm. And I claim this is equal to the supremum of, well, okay, here's T. And this is exactly the flat norm of T. Okay, and so psi is the curl of phi. And so then L acting on psi is this integral of phi dot T. And the norm of psi is the same as the normal curl of phi. And so this is the condition. The X norm is equal to the L infinity norm. Okay, and so my goal now is to extend, so Hombotic theorem. Is that there exists L tilde going from the big space, the whole space, to R linear, such that L tilde well, I should have written Y here. But it's Y endowed with the X norm. What happened to Y with the X norm? So Y is a subspace. Okay, is equal to L X, or sorry, Y to R, which is the thing we're interested in, the flat norm of T. Okay, so the Hombotic theorem guarantees that. And I claim that this is going to do what we want. So what is L tilde? So here's the point. So the Riesz representation theorem says that, well, L tilde, it's a bounded linear functional on continuous vector fields on R3 who decay infinity. And according to the Riesz representation theorem, that's exactly a vector value measure. So X, the dual space, is equal to, or can be identified with vector value measures on R3. So if I combine these two, there exists a linear function that can be identified with a vector value measure. So there exists some, let's call it nu. I'll use this measure notation for measures on R3, taking values in R3, such that, what did I forget to say when I was quoting the Hombotic theorem? I forgot a crucial thing. I forgot to say it extends extending L, right? It agrees with L on the subspace. So there exists a nu that such that L tilde of phi is phi dot nu of dx for all phi in, let's call this psi, in X And so what property? Okay, so it's a vector measure. It coincides with L on when it acts on curls, and so L tilde of the curl of phi is L of phi. So it is L of the curl of phi, i.e. So L of the curl of phi by definition is phi dot t of dx, and by what we've just said, this is, sorry, curl of phi. No, by definition we have this, and L tilde by definition, or by what we just said, is curl of phi dot nu of dx. Okay, and so this is, so I've just written down the statement that L tilde extends L, and that says that T is the curl of nu, and 3, the norm of L tilde, is equal to the norm of L, which is the flat norm of T. The norm of L tilde, on the other hand, is just the total variation of the vector field nu, of the vector measure nu. Okay, and so this shows that this shows the other inequality, the flat norm of T is greater than or equal to the infimum of nu of R3, where the curl of nu is T. Okay, so a couple of comments. Again, this is kind of a standard application of the Riesz representation, but it's interesting. It's nice if you haven't seen it before. And okay, the geometric meaning is a bit opaque because I wrote in terms of vector calculus. If we spent more time developing geometric measures here, I would write boundary instead of curl, and it would look more reasonable. And so, but whenever you see the curl of nu, think of the boundary of nu. And so the picture, and so the geometric interpretation is given in this picture. If I'm applying this to a difference of currents, this will tell me the area span between them. Okay, and so then, and this is a special case of a much more general theorem, which could be stated in terms of currents and forms and so on. So there's a flat norm acting on, well, anyway, but the idea is the same. The idea is totally the same. Okay. So this is what we've just done. And so here's the continuity. I said I want to study continuity properties of weak solutions. And I want to express them in terms of this flat norm. So here's the continuity statement. And so let me recall, I've been a bit vague about this, but recall a weak solution we define to be is a Orient Variable a family of indexed by T where T is in some time interval, some interval I is a interval. Okay, satisfying some conditions. So Orient Variable is just the kind of object it is. Closed and this balance law chiefly, and then given V sub T, we define, and so for any time this V sub T is a measure on R3 cross S2, where R3 records this position in space and S2 records the tangent directions. And so given this V sub t, we define the associated current T sub V sub t, which is, so this is a measure on R3 cross S2, and this is a vector value measure. On R3. The varifold is a bit mysterious. It has this piece down here in R3 and this other piece that we can't really see. The T sub t is what you really see if you're looking at the object. If you're watching the video on YouTube, what you see is this thing, is the T. And this is, it acts on vector fields by phi of x dot xc dv sub t of x and xc. So it's like the first moment in the with respect to the variables. Anyway, this is the geometric object that you would see the curve moving around. And so the lemma says, okay, we don't know so much about what's happening upstairs with these mysterious varifolds, but if we actually watch the curves moving, it says that if I look at an interval of size t, then the homogeneous flat norm difference between the curve at, I look at it from time s to time t, and the homogeneous flat norm, in other words, the area, the minimum area spanned by the curve at time, the difference of the two curves, scales like the square root of the time. Okay, so this is a very natural, so this, going back to the picture above, we're redrawing the picture. This says that the area here scales like the square root of the elapsed time if I have the curve of 2 times. Okay, and so what I'll do is I want to sketch the idea, which is very easy, and then I'll yeah. So here's the sketch of the idea. So here's the idea. I'll prove something weaker. Okay, I like this flat norm because it's geometrically natural. But if I'm just interested in easy stuff and getting some analytic insight, so the flat norm is the norm that's dual to, in terms of scaling, it's like, well, so it's dual to this L infinity norm of the curl, which in terms of scaling is like being dual to the just the L infinity norm of the gradient. And so I'll prove that the supremum of t at 2 different times the supremum of this thing Okay, so I've replaced the curl by the whole gradient. If I strengthen this norm, that's like weakening the dual norm, weaker but easier. And actually, the whole proof isn't that hard, but we don't want to spend too much on this. And so, so let's do this. So here we have helpfully recorded the definition, and my assumption. Let's make sure I. So my assumption is, all I'm assuming is, okay, so very weak binomial control is just the stuff in the box down below. And I assume that so this says, if you like, the generalized arc lengths are uniformly bounded by this number m. Okay, and so what do we have? And so first, if Well, so by definition, so what is this? This is exactly t acting, t sub t acting on phi. This is what I have on the left-hand side here. Right? And so by using the definition, I find that the integral from S to T of, let's give it a different name. T sub tau acting on phi d tau is this stuff on the right-hand side. And so here I'm imagining, I just fix some test function phi. And for here it should be C2 with convex support. And I didn't emphasize this before. And so if we look at the definition, I assume that I assume what I need to be able to apply the fundamental theorem of Cox, which I'm about to do. And so I assume that this map is the map that takes time into T sub T acting on phi is Lipschitz continuous, and that this identity, this differential equality holds almost everywhere. And so that's good enough to integrate. So I can integrate from S to T, this stuff. There's a minus sign. Okay, and this is clearly less than the second derivatives times, okay, so the integrand is, these x's are unit vectors, they're bounded by 1. And so this integrand is just bounded by the second derivative, and then the amount of the integral is bounded by m. M is the upper bound for this thing, for the mass of the variable. Okay, and also, and then that's multiplied by t minus s. So for every time I have this bound on the integral over x and c, and then I integrate it in time. And also, so this of course is t. Okay, on the other hand, the same thing, t v t minus t v s acting on phi. It will be bounded by the phi c0 times m times 2, I guess, right? So it's bounded by okay, this is absolute value. This is a okay, there's a factor of 2. So I have so t v sub t acting on phi. So I would write this as the sum of t v sub acting on phi and t v sub acting on phi, break into 2 pieces. And then each of those is bounded by phi times m, just by the definition again. And so what do I do? And so by basically by interpolation, if I have bounds on, okay, so I guess we do this like this. So I'll break this into 2 pieces. As usual, so t minus tvs. And so I'll have a phi epsilon plus phi minus phi epsilon, where phi epsilon is a regularization. Okay, and so, and eta epsilon is as usual a convolution on an epsilon scale. And so we can check that if I, well, what do you think? What do I want? I want this. So I have a smooth piece. So the idea is a smooth piece here and a small piece there. I'd like to estimate the smooth piece using the this. So if phi is only in C1, then phi epsilon will be in C2. I want to estimate the smooth piece using the first inequality. I'd like to estimate the small piece using the second inequality. And so for phi epsilon, I need to compute the second derivative. And then I need to also know phi minus phi epsilon, the small piece. What goes in the question marks? What do you think? So think about it for a second while I get myself a new piece of paper. Okay, and so if I average, if I have a Lipschitz function and I integrate it if I average on balls raised epsilon, then the difference between the average thing and the unaveraged thing will be of order epsilon. And then sort of similar computations have a 1 over epsilon here. And so, so what do I do? So T, let me write this in a quicker form of phi epsilon plus the same thing, acting on the difference. This is bounded by, I use this inequality. And so by 1, the first term is bounded by the T minus S times M times the second derivative of phi epsilon, which is 1 over epsilon times this. And the other term is bounded by just 2 times M times the L infinity norm of this thing, which is epsilon times grad phi infinity. And so now I choose, I optimize an epsilon. I choose epsilon to be the square root of T minus S. And then I find this is bounded by a constant times T minus S times the grad phi infinity. Okay, and so just these easy considerations, so kind of sort of trivially, the point is here, if I look at this definition, I can see if I act on C2 test functions, then the right-hand side is always bounded, and so the left-hand side is changing in a way that is changing linearly in time. Okay, and so this will tell me that if I then restate this in fancy language, this says that the measures are evolving in a Lipschitz continuous way in the function dual to C2. Okay, and then on the other hand, the measures are always bounded. So I have this linear in time growth in the dual to C2 norm, and I have this uniform bound in the dual to C0 norm, and so I get a square by interpolation. I get a square growth in the dual of C1. Okay, and if I just care about continuity, I already have that in the dual of C2, and so in some way. But I like this. I like the dual of C1 because it has this. Because if I strengthen it a little bit to the dual of curls in C1, then I have this geometric interpretation. Okay, and so the actual proof is like this with a little bit of technical messing around to replace the gradient here by the curl. And I've written it here. I've written a sketch, and I don't really feel like going into details. So we'll skip that. Okay, let me then say, so very quickly, existence of solutions. And so in this framework, one can prove easily existence of solutions of the binomial curve flow well, okay, so here's the existence theorem. So for any Lipschitz curve, any closed Lipschitz curve in R3, I can solve this binomial curvature. There exist solutions of the binomial curvature flow. And let me then show you quickly a video. So here's an example of a closed curve. You can see, I want to take this as an initialator for the binomial curvature flow. The curvature is 0 on the faces of the triangle, and it's infinite and it's a delta function on the edge of the triangle. And so let's see what's going on. Okay, that didn't work. Come on. Okay. I don't know why that. So I can't. Oh, here it is. Good. Okay, good. And so and so you see, if you program your computer to solve this equation and you give it this crazy data, it behaves kind of reasonably. I mean, it doesn't behave totally reasonably, but it has interesting behavior. And so the theorem just quoted says, well, what one is doing here is reasonable in the sense that there are actual solutions of the binomial curvature flow for this data. You can see this has all this, there are all these funny, interesting conjectures about how these behave. And so then in 3 minutes, because I don't want to spend too much time on this, let me say what's going on with this proof. And so the point is, well, so first of all, we have a proposition which is that a limit of weak solutions is again a weak solution. In other words, if I have a sequence of very weak solutions, again with, so when I define a weak solution, the definition of weak solution includes a uniform bounds on the mass of the curve. For a very weak solution, I didn't put that in the definition, and so I have to put it in by hand in the assumption. But so this implies in particular to what I call weak solutions. Okay, if I have a sequence of very weak solutions or weak solutions with uniformly bounded mass, and they converge in the natural sense weakly as measures to a limit, then that thing is again a weak solution. And the point here is just that, well, look at this. All these definitions are just these measures appear continuously here and here, and also in here, if you remember that. And so, so these just involve integrating the measure against test functions. If I pass limits, well, that I can do that with weak conversions. That's what weak conversions lets me do. And so it's almost, it's close to being trivial that, I mean, there's some subtleties, but it's close to being trivial that the limit of weak solutions is again a weak solution just because the measure appears linearly in the formulation of a weak solution. And so then what one can do to prove the existence theorem is we take a Lipschitz curve, regularize it, smooth it in some way, modify it, appeal to known theorems to get global existence of a smooth solution for that regularized curve, and pass limits and get a limit who is again a weak solution because limits are always weak solutions. This isn't so relevant for Euler, but there is a very general existence theorem in this setting. You don't expect to have uniqueness. Well, for example, I gave this example of two circles who collide and then vanish. Another solution with the same initiative is two circles who collide, then just pass through each other without seeing each other. That would be a weak solution. Or I could have two things who collide. I don't allow the mass to increase, but I could have them collide here, and then at the same moment, a pair of circles are born someplace else and move away from each other. And so let me see. That would appear to violate the continuity in time thing I just proved. Right, I said that the curve at time t, or the object at time t, which might be union curves, and the object at time s, that those evolve continuously in a certain way. But you see, if these things collide and vanish, then at this moment their flat norm is 0. And then if they're born someplace else, again at that moment the flat norm is 0. And so this pathological behavior, unfortunately, is totally consistent with the continuity in time estimate I just proved. Okay, I see there are a couple of questions. I'm out of time also.